Suppose we have a charged particle of charge q and mass m in the presence of an electric field E and magnetic field B. The equation of motion of such a particle is given as m d square x vector over dt square equals qe, which is force due to the electric field, plus qv cross b, which is the force due to magnetic field. So this is a vector differential equation, which means it is a set of three equations for three components of the position vector, and this equation can actually be derived from a Lagrangian L as Euler-Lagrange equations, and this Lagrangian is given as 1/2 m v square, which is the kinetic energy term, plus q v dot a. Here a is the vector potential, minus q phi. Phi is the scalar potential. The relation between vector potential and scalar potential with electric and magnetic field is given by these equations. Magnetic field is curl of the vector potential, and electric field is minus gradient of the scalar potential phi minus, if the vector potential explicitly depends upon time, then del A over del T. So this is how the vector and scalar potential are related to electric and magnetic fields. And the Euler-Lagrange equations corresponding to this Lagrangian will give rise to this equation of motion for a particle of mass m and charge q moving in an electric and magnetic field, which are given by these potentials. In order to see that this Lagrangian actually gives rise to these equations, let us first denote the position vector x as x1, x2, x3, and velocity vector as x1 dot, x2 dot, x3 dot. With this notation, the Lagrangian can be written as 1/2 m x1 dot square plus x2 dot square plus x3 dot square plus q x1 dot a1 plus x2 dot a2 plus x3 dot a3 minus q phi. Now the Euler-Lagrange equations corresponding to this Lagrangian are a set of three equations, and they are given by d by dt del L over del xi dot minus del L by del xi equals 0 for I equals 1, 2 and 3. These are the three Euler-Lagrange equations corresponding to these Lagrangian, and we want to show that these are the same equations. As you already know, this particle follows in the presence of electric and magnetic field. We will show this only for the x1 component. For the x1 component, if we first calculate del L by del x1 dot, then we get m x1 dot plus q a1. And if we calculate del L by del x1, then we will get q x1 dot del a1 by x1 plus x2 dot del a2 by x1 plus x3 dot del a3 by x1 and minus q del phi by del x1. Next we calculate the time derivative of del L by del x1 dot. This is given by double derivative of x1, which we denote by x1 double dot. So double dot notation stands for d square x1 by dt square. So we get m x1 double dot plus q total time derivative of a1. If we assume that a1 is a function of x1, x2, x3 and also time, then dA1 by dt will be equal to partial derivative of a1 with respect to x1, then dx1 by dt, which we denote as x1 dot, plus partial derivative of a1 with respect to x2, x2 dot, plus partial derivative of a1 with respect to x3, x3 dot, and finally partial derivative of a1 with respect to time. So this is the total time derivative of del L by del x1 dot, and if we subtract del L by del x1 from it, we will get the Euler-Lagrange equation corresponding to the coordinate x1. So d by dt del x1 dot minus del L by del x1 is given by mx1 double dot, this term here del a1 by del x1, x1 dot will be cancelled by x1 dot del a1 by del x1, and we will be left with q x2 dot. We take x2 dot common, and then we'll have a1 partial with respect to x2 minus a2 with respect to x1 plus q x3 dot del a1 del x3 minus del a3 x1, this term here, and plus q del phi by del x1. We also have this q del a1 by del t. So this is now equal to mx1 double dot plus qx2 dot, and if you look at this term, then this is if we write down the curl of a j k del by del x1 del by del x2 del by del x3 a1 a2 a3. Then you can see that del a1 by x2 del a1 by x2 minus del a2 by x1 is negative of the third component of curl of A. So this is negative of the third component of curl of A. And qx3 dot, this term is the second component of curl of A. Del a1 x3 del a1 x3 minus del a3 x1. So this is the second component of curl of A. This is second component of curl of A. And then we have these two terms, q del phi by del x1 and plus del a1 by del t. So now we get mx1 double dot. Magnetic field, as we have seen before, is curl of A, and electric field is minus gradient of phi minus del A by del t. So we have now plus plus qx2 dot, this is minus b3, the third component of the magnetic field, because B is curl of A, plus qx3 dot, curl of A second component means B second component, plus q, this is the negative of the first component of electric field, so this is minus E1. Therefore we now have mx1 double dot plus q x3 dot b2 minus x2 dot b3 minus q e1. Now if we look at this term and we look at the curl of B, not curl of B but V cross B, if we look at V cross B, I j k x1 dot x2 dot x3 dot and b1 b2 b3, then x3 dot b2 minus x2 dot b3 is the first component of V cross of B. So this is equal to the first component of V cross of B. So now we have our equation. The first Euler-Lagrange equation becomes mx1 double dot plus q V cross of B first component minus q e first component equals 0. this is our Euler-Lagrange equation corresponding to the x1 coordinate, which is the same as the equation of motion that we have written initially. So if we take the first component of this equation of motion, we will get mx1 double dot equals q, first component of the electric field, plus q times the first component of v cross of b, which is the same as this equation, except that we are getting a negative sign here. V cross of b, why we are getting a sign is this v cross of b first component. So if we take I, j, k, x1 dot x2 dot x3 dot b1 b2 b3, then this is x3 dot b2 x3 dot b2 minus x2 dot b3 minus x2 dot b3. So this is the negative of the first component of v cross of b. We have a minus sign here. This is the minus v cross of b first component. So the Euler-Lagrange equation becomes mx1 double dot equals q v cross of b first component plus q e1. Similarly, we can verify that the Euler-Lagrange equation corresponding to x2 and x3 coordinates will be same as the equations corresponding to x3 and x3 coordinates, x2 and x3 coordinates in this vector differential equation. One important thing that this Lagrangian has, an important property of this Lagrangian is that it depends upon the potentials. Electric, instead of depending upon electric and magnetic fields, this depends upon the vector potential A and the scalar potential phi. And this dependence has consequences when we quantize the theory. And one important effect that this leads to is called Aharonov-Bohm effect. We will talk about this in a future video.